Hello and welcome to the fourth part of Lesson 6. In the previous part of this lesson, we examined how to solve the energy equation for a simplified film casting operation. We examined three different heat transfer cases, two of which involved cooling by forced convection. For these problems, we were prescribed a value of the heat transfer coefficient. For normal engineering problems, however, we aren't usually quite so lucky as to be given a numerical value of heat transfer coefficient a priori. So what I'd like to do in this part of this lesson is start by asking a somewhat pertinent question when we're dealing with convection heat transfer. And that question is, how do we get values of H to solve practical problems with? In the previous part of this lesson, we sort of made a sweeping assumption. We said, your natural heat transfer convection coefficient, or your forced convection heat transfer coefficient, is 50 watt per meter squared Kelvin. How did we get that value? Is it even reasonable? For a different problem, how do we get a value of H? And that's what I want to address now. And the answer lies in convection correlations. Now, as you've studied heat transfer before, you've almost certainly come across convection heat transfer coefficient correlations previously. They involve Nusselt numbers, Reynolds numbers, Prandtl numbers, Grashof numbers, and they vary depending on what geometry you're looking at and what flows you have within that geometry. So, what we need to be doing is being careful to ensure that the various dimensionless numbers we are evaluating are for the correct material and for the correct temperature. Now, in the time I have available here, I'm just going to cover a few relevant scenarios, relevant to polymer processing. So I'm going to look at forced convection cooling of flat plates and cylinders, and we can make the analogy that these geometries are similar to maybe the air quenching of, say, cast film or spun fibre operations. I'm also going to look at natural convection cooling of horizontal and vertical plates and cylinders, and this could be, for example, like injection mold cooling or Parison cooling or water bath cooling, all of which are helpful to us when we're thinking about the design of polymer processing operations. So let's make a start with forced convection along a flat plate. So I'm going to draw a diagram every time when I'm thinking about this to assist the explanation, but also to assist the mental model that I have with each of these processes. So there is my planar geometry, my flat plate. I'm defining a coordinate direction, x, it's along the length of the plate, and I'm defining a surface temperature that I am allowing to vary as a function of length, Ts of x. Now imagine my, for example, fluid flow. This might be a liquid flow, it might be an air flow. So that, for example, airflow is going to be along the length of the film, and I have a far field velocity and a far field temperature, V infinity and T infinity. And what I'd like to do is to figure out, given my surface temperature of my film, given the far field temperature and velocity of the air, what heat transfer coefficient does that result in? And one can work that out with this integral expression here. Now let's examine this expression carefully. Let's have a look at what dimensionless groups are involved. We can see there in brown is the Nusselt number, HL over K, just rearranged somewhat so that H is the subject of this equation. In green we have the Prandtl number, mu Cp over K. And in red we've got the Reynolds number, V infinity rho x over mu. All of these dimensionless groups are raised to various powers. And we need to be careful that these correlations are valid for the fluid conditions we're looking at. This is valid if the Reynolds number is less than 10 to the 6. Now, back to being careful. We are evaluating the Reynolds number and all the other physical and thermal properties for the fluid, for the air if we're cooling with air, for the liquid if we're cooling with liquid. So the thermal conductivity K relates to the air. The viscosity, mu, relates to the air. The density and heat capacity, ρ and Cp respectively, relate to the air, not the polymer. And we're evaluating these fluid properties at what we term a film temperature, Tf. Now our film temperature is effectively the average between the surface temperature, Ts, and the far field temperature of the fluid, T infinity. So we know that there's variation of all these thermal properties with temperature. We can see from the integral expression that actually it varies with length. And so if we're solving this equation rigorously, then we're going to have to be incorporating this heat transfer convection correlation within the solution of the energy equation, and it's going to be a numerical solution. However, we can actually simplify this to get a good estimate, and maybe that good estimate is fit for purpose, because we can say, look, if my thermal properties of the fluid don't actually vary a great deal with temperature over the range of temperatures that I'm likely to encounter, then I can simply make that integral expression independent of everything other than distance x. And if we look at where that distance x manifests, we have it in the denominator of the Nusselt number, highlighted in brown, and we have x to the half in the numerator of the Reynolds number, highlighted in red. And if we think about that, this effectively becomes an integral of 1 over root x, which gives the result I've shown there on the board. And so we can see now that my heat transfer coefficient, h, is effectively independent of length, x. It is dependent on the length of the geometry that I'm looking at, and it is dependent on the thermal properties of the fluid surrounding that plate. For example, for air quenching, it's the thermal properties of air. And, moreover, because I've said that my thermal properties are effectively independent of the film temperature over the range of film temperatures I'm likely to encounter, that gives me just a constant value of h. And so, relating back to the previous part of this lesson where we said, oh, h is 50 watts per meter squared Kelvin, this is a kind of expression we could have used to generate that estimate. Alright, so that is forced convection cooling along a flat plate. Let's look at some different heat transfer scenarios. Let's say what we have is forced convection cooling across a long cylinder. And this might be, for example, how we quench spun fibre. We can imagine that we've got our fibre spinning die, our spinneret. We've got lots of cylinders, effectively, approximately, of polymer melt extruding from that spinneret, and we've got a lateral airflow across those spun fibres. So, in this case, what we find is that we've got different correlations for a liquid being flowed laterally across that geometry, and for a gas being flowed laterally across that geometry. So for the liquid, we can imagine this is quench cooling in a water bath, for example. For a gas, we can imagine it's quench cooling with an airflow. Now, let's pay very close attention to the subscripts in each of these correlations. Subscript infinity means that the group or parameter is evaluated at the far field temperature, T infinity. Subscript S means that it is evaluated at the surface temperature. Subscript F is evaluated at the film temperature, which is half of the sum of the surface and far film temperatures. So just be very careful what temperature you're using for each of the parameters or groups you're evaluating. So if we look at the liquid case, we can see that we've got two correlations. We've got a laminar flow correlation over a range of about 1,000 Reynolds number, and we've got a turbulent flow correlation. And so again, make sure that you know what flow regime your quenching medium is actually obeying. So there on the board, I've now put the same expressions as pertinent to gases. So we've got a laminar flow case and we've got a turbulent flow case. And we can see there's some similarity between the gases and liquids and some differences. So again, we just need to make sure that we're using the right correlation for the right geometry under the right flow conditions. Alright, let's think about natural convection cooling, because sometimes we do this, maybe in injection moulding, maybe in Parison forming. So let's think about natural convection cooling of a vertical cylinder and a vertical plate. Let's think of the mental model of what's actually going on here. If we've got natural convection cooling, what's that all about? Well, we've got a liquid flow or an airflow driven by buoyancy differences, because let's assume we've got a gas. As that gas warms up, it gets hot and it will rise. So the gas next to the hot object is going to warm up by conduction. That gas will rise and you'll get a naturally convective airflow or fluid flow next to the surface of the hot object. And that is what is driving the heat flow in this particular case. So, if we're thinking about natural convection, we need to somehow quantify the buoyancy of the fluid external to the hot object. And we can do this with yet another non-dimensional group, the Grashof number. The Grashof number is a statement of buoyancy forces divided by viscous forces. So we can imagine if we've got an essentially inviscid fluid, for example air, and we've got a large density change with increasing temperature, then the buoyancy forces are going to be quite high. If we imagine we've got a similar change in density due to temperature difference, but a very viscous fluid, we can imagine that the Grashof number is going to be quite low. And so again, we can get a mental model as to the extent of that natural convection circulation based on the physical properties of the system. Now, let's have a look at the Grashof number in a little more detail. We can see that it involves a length scale. Now, my length scale changes depending on whether I'm dealing with a cylindrical geometry or a planar geometry. For my cylindrical case, my length scale is the diameter. For my planar case, my length scale is the total length. We've got other parameters there that we might expect for a buoyancy-based calculation. We've got density. Density will change. We've got gravity. That's going to kind of be important as well. We've got viscosity, because the Grashof number is the ratio of buoyancy to viscous forces. We've also got a parameter beta here, which is the amount that my fluid expands with respect to temperature. And we can estimate beta for gases as being 1 over absolute temperature. And then for two liquids, a polar liquid and a non-polar liquid, for water and for paraffin, as about 2 or 7 times 10 to the minus 4 per Kelvin, as measured at 20 degrees C. So we can get an estimate then for what my Grashof number actually is. And then I can use a Nusselt number correlation based on the product of the Grashof and Prandtl numbers evaluated at the film temperature in order to get an estimate for my heat transfer coefficient. And bear in mind the range of validity for this correlation over a range of the product of the Grashof and Prandtl numbers. Okay, let's think about natural convection cooling now for horizontal objects. It's going to be somewhat different to a vertical object, because we can imagine on a vertical object that airflow that's instantiated next to the object is going to be rising up that object all the time, and so the gas is going to heat up quickly at the bottom and then maybe be less effective at cooling as it rises because it's already quite hot, and so the temperature differential between the hot object and the gas next to it moving by natural convection is perhaps not as great as it could be. With a horizontal object, the gas or liquid is going to be moving upwards and away from the object at all points along its length. And so we might expect a horizontal object to cool a little better, maybe. Again, the convection correlations depend on the geometry. And so I'm going to look at a cylindrical geometry, lying flat, and a planar geometry, lying flat. As one would expect, the Nusselt number correlation depends on the Grashof number, because we've got buoyancy involved. And as before, it's actually the product of the Grashof and Prandtl numbers. Now, the thing to be careful with here is how we determine our length scale in the Nusselt number. So for our cylinder, our length scale is simply the diameter. But for our planar geometry, my length scale is a combination of the length and the thickness of the object that we're examining. Okay, so we've spent some time in this part of this lesson talking about correlations. And there are many, many, many more of these that you can go and look up in, for example, Inkrepera and DeWitt, which is one of the heat transfer handbooks. How do we use these things? Assuming that now we can obtain the correlations that we want to get the heat transfer coefficients that are pertinent to our problem, how do we use them in a calculation wisely? All right, let's have a look at that in relation to this diagram. This is a very, very simple polymer processing operation. I've got, for example, a cast ribbon coming from a die. It's a planar cast ribbon. It's going into a quench tank. There's a certain residence time in that quench tank, and then the material's being hauled out of the quench tank, it's being drawn down and it's dried. Alright, well, let's concern ourselves with what is likely to be the dominant place where heat transfer occurs. Let's say it's as the material is travelling along the length of the quench tank between point 1 up until point 2. What I might do is say, well, okay, at point 1, let's calculate a film temperature. Let's say there's been negligible cooling happen till then. We know for air cooling there's going to be advection dominance, and so very little cooling occurs. So let's say at point 1 it's effectively somewhere near die temperature, especially if I start at the water surface. And at point 2, I might be designing this to try and quench something, so I might make an estimate roughly of what I might expect the temperature to be, and then I'll go back and check that later based on how much heat I've lost. Okay, so if I've calculated my film temperature at point 1 and point 2, I can therefore calculate my convection heat transfer coefficient for maybe forced convection and natural convection at point 1 and point 2. And if I calculate the forced and natural convection heat transfer coefficients at 1 and 2, I can see which is the biggest. What's going to be the dominant mechanism? It's probably going to be forced heat transfer. So I can therefore choose the largest value of heat transfer coefficient based on what is likely to be occurring. Then what I might do is take an average value of H at point 1 and point 2 and do my first heat transfer estimate. That will yield how much the film has cooled between point 1 and point 2. Which means I can therefore go back and check to see whether that initial guess of H at point 2 is sort of in the right ballpark. Then I might go through this procedure again with an updated value of my average heat transfer coefficient based on that new value of temperature at point 2. And then I'd go through down to point 4 and look again and say, well, actually, yeah, that's quite close, but I'll go through one more iteration, updating my film temperature with my new temperature at point 2 until I'm satisfied that actually it's pretty close and it's good enough to answer the problem I'm trying to solve. Of course, another way we could do this is entirely numerically. And if we're constructing a numerical solution, we can build in the temperature variation of the physical properties as part of the problem that we're solving and solve what is actually quite a complex coupled differential equation or set of differential equations right at the get-go, such that H is always depending on T, T is depending on X, T is also depending on the value of H, and so we've got this coupled set of equations that we can solve where we don't actually have to manually iterate to a solution. It's a little more complex to do that, perfectly tractable using solvers such as Mathematica, but also we have to ask ourselves the question, what problem are we solving and to what precision do we actually want to know the answer? There's times where that rigorous numerical calculation is exactly what's needed. Conversely, there's times when a quick calculation analytically based on estimates is absolutely fit for purpose. So don't forget to always be aware of the precision you need to know the answer to. All right, let's summarize a few key points. We've looked at how to obtain numerical values for heat transfer coefficients, and it's by correlation. And the correlations depend on a given geometry and also a given heat transfer scenario. We've seen when we've discussed these correlations that you must be careful to use the correct temperature to evaluate the thermal properties of the fluid. Is it the far field temperature? Is it the film temperature? Or is it the surface temperature? We've also seen that there are many different correlations out there. We've looked at effectively 4 or 5, but if those aren't relevant to the problem you're trying to solve, do have a look at, for example, Increpera and DeWitt or other heat transfer resources, and you'll be able to find lots more correlations that might be more applicable to the exact problem that you're solving.